Alright, so in this video we're going to talk about equivalence relations and equivalence classes. An equivalence relation is very simple. Equivalence relation is simply a relation that is reflexive, symmetric, and transitive at the same time. So it's pretty easy based on our previous discussions to verify whether or not you have an equivalence relation. You just check for whether or not your relation is reflexive, symmetric, and transitive, and we did that multiple times, and you should have done lots of exercises where you did those things. And then there's this new idea of an equivalence class. Equivalence classes. So these brackets are used to indicate an equivalence class, and basically, so the equivalence class of A is basically just a list of all elements from our set X that we define our relation on. It's a list of all elements that are related to A. So I think let's take a relation and look at an example. So here's a relation, got the elements listed out, and you could go through and verify that this is an equivalence relation, meaning that it is reflexive, symmetric, and transitive. And so we might want to list the, and I did not clarify, this is defined on the set. Let's see, 1, 2, 3, 4, 5, 6. So we can go through and list the equivalence class for each of the elements in the set X. So if I just use this piece of my definition, that's really what we need. So the equivalence class of 1, I'm just going to plug into this definition, right? So if 1 is here for A, then I would plug 1 there for A. So that's going to be all elements from my set X, so that those elements are related to 1. Or in other words, we use this notation, right? We're looking anything that's related to 1. So anything that has 1 as the second number in the ordered pair. So let's see. 1 is related to 1, so it's in the equivalence class. 3 is related to 1. It's in the equivalence class. 5 is related to 1. So it's in the equivalence class, and it looks like that's all. Right, and we can do the same thing for the, let me erase this and get that out of the way. The same thing for the equivalence class of 2, now that we know what it means. Anything that's related to 2. So 2 is related to 2. 6 is related to 2. So its equivalence class consists of just 2 and 6. And so we can do the same thing for the element 3. So let's see. 3 is related to 3. 5 is related to 3, and I missed up here, 1 is related to 3. So 1, 3, and 5. That's the same as the equivalence class of 1. Alright, so this is equivalent to the equivalence class of 1. Same set. Right, and then we can look at the equivalence class for 4. As I look through all of my elements in the relation, there's only one that involves any 4. Only 4 is related to 4. Right, and we can do the same thing for 5 and 6. Real quick, if you go through, look at the equivalence class of 5, you would find that that's 1, 3, and 5. Right, so that's the same as the equivalence class of 1. Same as the equivalence class of 3. So all 3 of those equivalence classes really are the same thing. And then last thing, everything that's related to 6, you would see that that's just the elements 2 and 6, so that's the same as the equivalence class of 2. Okay, and that's the basic idea of an equivalence class. This is something that pops up a lot in math and computer science, and it really is just a way of grouping the elements in your relation, a way of organizing maybe. Maybe you can see the organization a little better if you look at the digraph of the relation. So let's do that real quick. Now, if I look at the elements 1, 3, and 5, when I draw my graph, I've got to group those separately, right? Because 1, 3, and 5 are never going to be related to 2 and 6 or 4. All right, so I want to draw 1, 3, and 5 over here somewhere. And separately, I'm going to group 2 and 6 because 2 and 6 are never going to be related to 1, 3, and 5 or 4. And then 4 is kind of a loner by itself. Right, so what do we have? We have each of these related to themselves. That's true, I think, for every element. 5, 5, 6, 6, 2, 2, 4, 4, right? So every vertex is going to have a loop. And then, let's see, we've got 1 related to 3, 1 related to 5. We've got 3 related to 1 and 3 related to 5. And we've got 5 related to 1 and 5 related to 3. Okay, and then we also have 2 related to 6 and 6 related to 2. Right, we're expecting all this because if we verified that we had an equivalence relation, we expect that this relation's got to be symmetric. Right? So we're expecting that if we had an edge going one direction here, it's got to go the other direction as well. Right, and then 4 was only related to itself. Okay, so you can kind of see in the digraph, if you draw the digraph, these equivalence classes, right? Here's the equivalence class of 1, 3, and 5. Then here in the middle, you've got the equivalence class of 2 and 6. And then out here, the equivalence class of 4. So if you draw the digraph, the equivalence classes kind of separate themselves. You get a nice visual of the natural grouping, of the relation. Okay, so we're not going to do a ton with equivalence relations and equivalence classes. We kind of just want you to have a feel for what they are, and hopefully that's relatively simple idea.